Um, okay, I can go ahead and start sharing my screen. Um, um, oh wait, no, sorry. Okay. Are you able to see this?
Yes.
Okay. Okay, great. Well, I'm ready whenever you are for the recording. Okay. Did it? Okay. Okay, I can go ahead and begin. So welcome to Berkeley Pharma Tech Sustainable Farming Team Research Presentation. My name is Adrita Chatterjee. My group members are Preston and Andrew, and our research centers around potential solutions related to farming that kind of will help repair damages to the environment and to climate change. And our aim specifically is to take advantage of the natural processes that work to mitigate climate change, since man-made efforts have a lot of adverse effects, such as pollution. Yeah, so um, okay, so yeah, there are a couple modern agricultural practices that kind of contribute contributes dangerous amounts of CO2 into the environment. Some examples are tillage and synthetic fertilizer overuse. And while these practices were initially considered beneficial because of greater food production for lower cost, it's not until recently that the negative effects of these practices were really understood. And they already add more CO2 to an overly CO2 filled atmosphere, and which exacerbates damages from greenhouse effect. And so CO2 is essentially a greenhouse gas, which traps the heat absorbed from the sun, and the amount of CO2 has risen roughly 1/3 since the Industrial Revolution, which is a spike that we're able to see on the following graph. Okay, so sorry. Yeah, so basically, as you can see, from over the past couple of years, there's been a large spike in the amount of CO2 in our atmosphere. And this graph was created by NASA and illustrates that that this is not just merely a fluctuation that has happened, but this is a new kind of phenomenon that is happening that has never happened before in history. So the CO2 is measured in parts per million, as you can see on the y-axis. And so according to NASA, a safe amount of CO2 that we should see in the atmosphere is about 350 parts per million. But as shown on the graph, the current level is roughly around 410 parts per million. So from this graph, we're able to see that a potential solution to this problem is to extract CO2 from the environment, because simply just reducing carbon dioxide emissions will not be sufficient. Okay, so because of the warmer climate, you can see CO2 and climate change impacting all aspects of life, from glaciers, glaciers melting, that results in a lot of flooding of coastal regions. We also observe more extreme and intense major storms, and a lot of land experiences longer and more frequent periods of drought. Farmers have also called for change as growing crops become increasingly challenging on most eroded soils, and especially since water supplies have diminished, and areas where animals and plants can live continue to shift and decrease. So basically, the National Farmers Union released a statement in 2019 describing such challenges and called for more financial and technical support, strong policy mechanisms, and robust climate research. And in urban areas, urban environments where a lot of us live, the warmer atmosphere traps and increases smog levels, and overexposure to smog can cause serious health conditions such as asthma, heart disease, and lung cancer, which a lot of people in big cities have been experiencing over the past couple of years. Aside from health and environmental risks, the economic consequences of climate change pose another threat to a sustainable future. The BPT finance team was able to estimate that damages to power generation and transport infrastructure caused by natural disasters cost around $18 billion a year in low and middle income countries. On the worldwide scale, natural disasters have caused disruptions to households and firms in excess of around $390 billion a year. While the potential consequences of climate change are frightening, they have forced humanity to begin brainstorming alternative ideas and implementing efforts in order to mitigate climate change. Some of the proposed strategies involve nuclear energy, renewable energy, and biosequestration. So nuclear energy involves the use of nuclear reactions to produce electricity. Nuclear power can be obtained from nuclear fission, nuclear decay, and nuclear fusion reactions. But presently, the vast majority of electricity from nuclear power is produced by nuclear fission of uranium and plutonium in nuclear power plants. So while these could help mitigate climate change, they come with other drawbacks, such as different forms of pollution and unsustainable operating costs. These disadvantages can be avoided by focusing research on a strategy that exploits a natural process, which transfers carbon dioxide out of the atmosphere. So that would be biosequestration. And that is basically where carbon is captured from the environment and stored in soils through the use of living organisms such as bacteria and plants. Because this process naturally occurs, there's no expected adverse effects to occur if we exploit this process. And currently carbon is emitted into the atmosphere at a faster rate than it is sequestered into soils. So a lot of the research efforts aim to accelerate the carbon sequestration process so that carbon is sequestered at a faster rate than it is emitted, which will be beneficial to mitigate the harmful effects of climate change. So a lot of people in the scientific community believe we can solve a lot of our problems, climate problems, by enhancing the process of drawing carbon dioxide from the atmosphere and storing it in the soil. The Earth's soil is capable of storing an enormous amount of carbon, and its presence in soil improves crop productivity and quality. One of the primary reasons this strategy is receiving a lot of support and attention is because it describes a potential means of transferring the already elevated carbon dioxide levels away from the atmosphere as opposed to only reducing the carbon dioxide levels emitted into the atmosphere. So a lot of the biosequestration is based on a project drawdown. Carbon is not stored in soils as carbon dioxide gas. It is fixed and converted to sugar for plants and other organisms to use as energy source. So it is first absorbed from the atmosphere in plants, which is used to conduct photosynthesis. And as carbon dioxide is fixed into sugar, it is eventually transferred to other organisms like fungi that can be used to make new substances stored in soils, such as soil protein glomalin. So this chart shows the various ways that carbon is naturally sequestered from the atmosphere into the soil. So by researching methods to increase the efficiency of these pathways, we may be able to tip the equation of carbon emission versus carbon storage in favor of storage. And note that the arrows represent the transfer of carbon between different entities. And during our team's research, we've discovered that atmospheric carbon dioxide, shown at the top, can be moved to plants, which would be stored in the fungi, which would produce glomalin, which would cause soil to aggregate, which would sequester carbon. And that offers the greatest potential for human activity to make a difference. So that was the process that we are basing most of our research and our solution from. So in order to identify which pathway might offer the greatest promise, we first had to isolate the variables that most significantly contribute to carbon sequestration. So there's been a lot of prior research about glomalin, and in the Handbook of Climate Resilience, the author notes that glomalin is the main factor that influences the carbon sequestration and storage in soil, either directly or indirectly by influencing other carbon sequestration factors. And this is because glomalin attaches to soil particles and organic matter to form clumps that enable land area to resist erosion and degradation. And glomalin is produced by AMF, which is a fungi, which is in symbiosis with host plants, which we saw represented by an arrow in the previous slide. So identifying specific organisms that can enhance these interactions in these symbioses and increase AMF's production of glomalin is the main goal of our research, as it would increase carbon sequestration. So what we found was that plant growth promoting rhizobacteria possess different specialized functions that may be useful in enhancing these interactions so that more glomalin is produced by AMF, ultimately causing greater carbon sequestration. So for example, PGPRs that specialize in phytohormone production have been studied and shown to increase glomalin production, most likely by stimulating both plant growth and AMF branching. Phytohormones with these functions include indole acetic acid, sorry. Okay, so the basis that the couple of factors that are used in selecting these microorganisms include halotolerance, thermotolerance, drought resistance, and pathway dependent efficiency. So halotolerance is salinity tolerance, and a lot of these organisms have different selectivity for sodium sodium, and we see that through the different selectivity in the channels. Thermotolerance is tolerance to fluctuation in temperatures. So certain organisms are able to survive at higher or lower temperatures, which is another factor that we could select for. Drought resistance is a pretty obvious and self-explanatory characteristic. And finally, pathway dependent efficiency. So for example, using the phytohormone producing rhizobacteria, we're interested in which strains of phytohormone producing bacteria are most efficient in generating indole acetic acid, and the PGPR capable of producing the most phytohormone would be most beneficial to improving soil conditions. So finally, the commercial outlook of climate smart technologies. As you can see, the global market size was about $1.75 billion in 2019, and it is only expected to grow during 2020 to 2027. And a couple of the key players, including private and public players, include Hexas Biomass, which is a biomaterials company that focuses on using sustainable plant-based materials to replace wood and petroleum-based feedstock in multiple applications. And then we also have Carbon Engineering, which is a DAC technology, so direct air capture, which essentially just focuses on taking carbon dioxide out of the air. And public players include NRG Energy, which is just a carbon capture coal plant project, and Bayer, which works on reducing greenhouse gas emissions of crops, and helps farmers sequester carbon dioxide, while also reducing emissions from their own operations. So a couple of comparable approaches is that Hexas Biomass aims at producing biofuels, which would be advantageous in the sense that the carbon could be transformed into useful energy. However, a drawback is that there is a lot of ground pollution associated with this, which would cause this whole process to be counterproductive. And the other company, Carbon Engineering, mimics plant entry functions, which would be advantageous because it would accomplish the work of 40 million trees. However, the economics are only favorable at industrial scales. So to summarize our group's presentation and the research that we are doing, we have realized that the most viable solutions would rely in our soils. So our research focuses on enhancing natural processes that sequester carbon from the atmosphere to soils. And the human activity may be able to enhance these processes as a strategy to mitigate climate change. However, as we have seen previously, there are a lot of adverse effects to those, and specifically research into the effects of specific strains of microorganisms in order to increase glomalin production is crucial in order to repair the climate and put an end to climate change. These are our contact information if anyone wants to reach out and ask more about our research and what we're doing. And thank you so much for your time and listening to our presentation.
Thank you, Adrita. That was a great presentation. I do have a few questions for you, just primarily having to do with carbon sequestration.
Mm-hmm.
So I think you mentioned there that Glomalin
I
or
can
specifically?
just stop. Yeah.
Yeah,
Sorry.
so Glomalin or specifically the actions of a certain fungi that's inside the earth is going to help us with carbon sequestration. So like from your team's perspective, how do you see like just ways of amplifying these effects on, I don't know, just making the soil more favorable towards these fungi and so on and so forth?
Yeah, so based off of our research, we have found that different microorganisms um, stimulate and enhance glomalin production through different mechanisms. So certain strains of microorganisms stimulate glomalin as stress response mechanisms, and some PGPR produce phytohormones that enhance AMF colonization, and they increase the root surface area and susceptibility of the plant to AMF hyphae penetration, which all essentially just increase the glomalin. So there's different mechanisms, and other mechanisms, like I said, have selectivity for certain ions to pass, which would cause it to be more or less tolerant to salinity. So these are all kind of ways that glomalin interacts with its environment, with other microorganisms. So by studying these mechanisms, we have realized that we could cause stress responses essentially of the glomalin in order to produce more glomalin and sequester more carbon.
Yes, thank you, Adrita. So that was an excellent answer. Just as a just one last thing I'm curious about is like, so there's these fungi at working at the root of plants inside the soil. What are their foods exactly? What do they feed on?
Yeah, so a lot of these plants just they feed on like other microorganisms, other like bacteria. A lot of it is done through their energy is obtained through photosynthesis. So they have different ways to get energy from the environment, whether that be through the sun, or whether that be through other smaller bacteria and microorganisms.
Okay, great. Thank you so much.
Yes.
Um,
And yeah, sorry.